Okay. So good morning, everybody. Welcome to the third day of this conference. So today, first we have a panel discussion on what are the awesome things which lensing can do to search for dark matter. So we have 3 talks, and then we'll have a discussion. So the first talk is by Raghuveer Garani, who will talk about how to search for dark matter substructures using caustic lensing events. Go on.
Thank you for the invitation, and thank you for having me here. So in the past few days, we learned about how to detect dark matter in some of the talks if dark matter interacts with the standard model. So this will specifically focus on the fact that dark matter only interacts gravitationally to leading order. In fact, much of the evidences for dark matter comes from gravitational observations. So here the focus will be on dark matter substructure, in the sense subhalos, mini clusters, such things, how one can use gravitational lensing methods to constrain them. So in fact, gravitational lensing is now to date about 105 years old. The first lensing event was detected by Arthur Eddington, the deflection of sunlight, which people learn in their courses. And in fact, in 1930s, it was Zwicky who suggested that galaxies it was called extragalactic nebulae in those times. Today we call them galaxies. How galaxies can act as galaxies and galaxy clusters can act as gravitational lenses. After that, the field was little on the low side until about 1960s, when seminal works of Refsdal and Klimov worked out how strong gravitational lensing works. And that was on the theory side. But the greatest improvement came in 1979 when photographic plates in astronomical observation was replaced by CCD cameras. And soon after that, there were first lensing events of quasar discovered, strong lensing events, and from then the direction is only up. So we're seeing more and more of these things. And so what I spoke about was just a minute ago, the standard microlensing. But here I'll focus on something called caustic lensing. So I want to first tell you what is a caustic and how it comes about and how it's different from the standard microlensing, which most of you are familiar with. So when you look at a pool of water, you often see these corrugated structures. These are known as caustics, basically. And this happens because the density, the mass in the column is varying because the surface is not exactly flat, and there are ripples and waves. And that causes regions where you have high magnifications and regions you have normal magnification. So this is the day-to-day example, but there is a gravitational analog to this. I'll come to that. So this is the first caustic crossing events observed. So this was uncovered in Hubble Space Telescope data. In fact, they were not looking for it. It was discovered serendipitously. They were looking at something called supernova Refsdal, which is a very specific, strong gravitational lens. So you see 4 images of the supernova here, this so-called Einstein cross. And they were observing this. And they figured out there is one star, so LS1, very creative, it's called Lens Star 1, was seen in 2014 as a small, bright object. So this brightness lasted for about few weeks, and then it disappeared. And then it reappeared again in 2016, which was much brighter and lasted for several months. So the way to interpret this event is that, so this is something called a caustic curve, or this is a set of points in the source plane where when an object crosses through it, if you place the object exactly on top of it, you're supposed to get infinite magnification in an ideal calculation. Of course, this is broken by finite size of the source and the granularity of the lenses. So this was in fact predicted in 1984 by Pazinski and company, but discovered only in 2018. So how does this work? So if you look at the flux data, you see there are 2 panels. One spans, so the first data point is in 2004, and they're still taking this data. And you see that what you have to focus on are the black points, and I'll come to what the other curves mean. So the point is, it's a very specific light curve. It's an asymmetric light curve, meaning it has wiggles and slowly rises and rises sharply and falls dramatically. So this is a typical caustic lensing crossing event. So these models are different. The blue and the orange color curves, they correspond to different lens models and different hypotheses. So what fits well with this is the fact that, in fact, it is a caustic crossing event, and the lensing is caused by most likely so-called intercluster stars. These are faint stars. You don't see them bright, and the density of such stars in a typical galaxy cluster can explain these events. But in fact, using this, you can put a limit on dark matter as well. I'll come to that in the last part of the talk. So let me do some very quick theory. Yeah, they're embedded in the galaxy cluster. Intra-cluster star, sorry, yeah. So I'm sure most of you are aware of this, those who work in this sort of business. This is a typical point lens, point source lensing. So this is something called the lens plane, and this is the source plane, and this is the observer plane. And these are the typical distances. And the magnification is basically as the star is here. So this is the so-called Einstein ring, for example. If the star is inside the Einstein ring, you get a magnified image. And this is the famous lens equation, which basically relates these angles. Relating angles of the true source position with the apparent source position, and magnification is simply the ratio of those two, that is a derivative. So a critical curve is defined when magnification goes to infinity, so magnification inverse goes to 0. So for a point mass lens without granularities and so on, this simply corresponds to the Einstein angle. So if you place the source exactly at this point here, you will get a very bright image all over the lens, all over the ring. I'll show you I'll demonstrate that. So what is different here? So it's the same diagram, but slightly more colorful. So objects are moving, and here these lensings are typically, the typical lens scale of these lensings are gigaparsec. That's the effective distances, and probably redshift around half or 0.6 or such a number. These are the numbers you have to keep in mind. So formally, you can write the amplitude of waves you receive here given a source in this way. I'll not go into details, but what is the most important, so this is basically a path integral, and you can reduce it to, and this is basically the two-dimensional gravitational potential projected on the image. So hence the d2x. So d2x, because it's a two-dimensional image, so there is x1, x2, and similarly there's a two-dimensional plane on the source, so that's y1 and y2. And the information about everything gravitational is encoded in this time delay function tau, which looks like this. And this is basically the gravitational potential. For the point mass lens I was telling you about, this basically goes as 1 over x. But here we'll start deviating from that. So given the amplitude, magnification is simply amplitude squared, and the lens equation is obtained when you minimize this function, the time delay function. And you can do all that, but the specific point for the caustic is that to get an analytical handle on this problem, you have to expand this function around the critical curve. And the magnification analytically in a very simple scenario goes as an Airy function, and Q is related to the derivatives of the time delay function. And omega is, so all of gravitational lensing just depends mostly on this parameter, gravitational radius with this gm. There's an order 1 factor which I don't care about right now, gm over the wavelength. So here we'll focus on optical wavelengths and some sort of lens model. So this is the basic theory, and I can do a realistic simulation of this. So there is a code called Graphic by Oguri, so where they provide lens models. Basically these are two-dimensional tables where each point there's a value of a gravitational potential. So the critical curve is defined on the on the lens plane, and the caustic is on the source plane. It's the same thing projected. So this object you're seeing here that is going around is basically a source star which is moving. So as soon as let's wait for it. Oops. So when the source star comes within the caustic, you'll begin to see multiple images. Here two, one of them will be very bright, the other one faint. And as soon as it's exactly in the center, you see a big magnification. So this is an isothermal sphere. It's still not point mass. It's an isothermal lens. So for caustic, normally in a realistic situation, things are not isothermal. You also have something called gravitational shear, meaning this is gravitational potential perpendicular to your line of sight. So that basically deforms your nice circle into an ellipse. And that maps onto a particular set of points in the source plane, which has funny patterns. And as soon as the stars cross these points, the number of images changes and magnifications change. And all of this is basically, you see, depends on the motion. And the whole point is that here you look at time series data of stars and spectroscopic time series data. That's what you need to do anything in this business. So now let's put micro lenses on the uniform lens model. What happens then? So this you see is the old caustic curve for an isothermal lens. As soon as you put small granularities, you see deformations of this critical curve. They typically come out as particular geometric shapes. In this simple example discussed in this paper here, they describe how to get this analytically to some extent. And these are, so your smooth curve is deformed by gravitational potential there. So as a star, so when a star crosses through this, you'll have a very specific time series pattern depending on your lens model and how much granularities you put. So that's the basic idea. And here this is a simulated light curve for a source which is 100 solar radii, and basically the velocity of the star that is assumed here is 300 kilometers per second. So this is illustrative just to tell you how to do it. So on the left panel is a smooth lens. There are no granularities in it, and these are regions of magnifications. And so basically here the star is here. This is the image. As the star moves, like it'll move towards the caustic, and this is how the images move. And that corresponds to this dotted line here. It's a smooth curve, still asymmetric. It goes up and falls down. As soon as you add micro lenses on top of your big lenses, as I showed you, the critical curve changes, you get specific patterns. And on this projection, it looks something like this. There are regions where if you're here, you get large magnification. If you're just beside that, you get smaller magnification. And that gives you this very, some sort of a sinusoidal pattern with varying amplitude. That's the solid line here. And 1, 2, 3 corresponds to 1, 2, 3, those positions. And you see that it fluctuates like this, goes up and comes down. So how do we exploit this? The key insight is that the fluctuations, the variance of the power spectrum, the variance of the light curve here directly maps on to the two-dimensional power spectrum of micro objects if you want to do a theoretical calculation. You put these two things together to try to see if it's caused by dark matter. If not, put a limit. Okay. So I'll be focusing on QCD axion mini cluster. And we know that QCD axion is part of the standard model. And somewhere, I don't know where I heard it, it says it solves more problems than it solves. So the problem it solves are CP conservation. Of course, you make theta dynamical and you get this term. So at late times in the universe, it can behave as non-relativistic matter. In this case, it could be dark matter. Of course, the question is, cosmologically speaking, how do you produce them? So there are two scenarios, broadly speaking. One is called the pre-inflationary scenario, where the Petitquin scale is much larger than the Hubble scale at inflation or the maximum temperature in the early universe you can think of. But this is a very difficult calculation because you don't know the field value, very difficult to predict. So it makes relic abundance calculation difficult. Or basically, you can do anything you want and it's not too predictive unless you make additional assumptions. The scenario I'll be focusing on is the post-inflationary scenario, where the Petitquin scale is broken after inflation. So what this means is that we know it's a U1. So when it's broken, you're often left with a string network and domain walls. And these networks decay or annihilate, giving you some relic abundance values for axion dark matter. But the relic abundance is uncertain because this relies on, you have to simulate these string networks and extract the relic abundance. And the simulations so far, they only go in log of FA over Hubble, they only go like from 4 to 8 or 4 to 10. And we have to extrapolate to later times to get the relic abundance. But once you have the relic abundance, well, okay. Broadly speaking, this is the cosmology of the QCD axion. You can read this famous paper for all the details. So this is a plot in FA versus the Hubble scale Hubble scale during inflation, and you see much of the parameter space is constrained already. Most likely, the solid curves here correspond to a specific configuration. Like the solid curve corresponds to lattice results, and the dash corresponds to instant-on configuration. So much of it is excluded by isocurvature perturbations, but what is allowed is this region here. So here, axion can be dark matter candidate with 100% abundance. So on the y-axis, you see all these experiments. The solid curves you see correspond to experiments that assume dark matter, axion is dark matter, and they can draw a limit. And the dashed ones, they correspond to axion is not dark matter, you're just producing them somehow, and like helioscopes, for example, and those lie here. And then there are these other exclusions, which I'll not discuss too much, but we can talk offline. Okay. So how do mini clusters come about? So mini clusters, basically, as the universe expands, M8 depends on the temperature. So mass of the axion is related to details of pion. It basically goes as pion condensate at finite temperature over the vacuum, which is roughly T square over FA square times some Bessel function. And when the Hubble expansion rate, when mass is matched to the Hubble expansion rate at a given temperature, they start to oscillate. And at that point, you can have large over densities, which sets the mini cluster mass. This was discussed in seminal works of Karchev and Kolb. And the mini clusters decouple at a particular temperature, roughly around matter radiation equality. So typical densities is like 10 to the 3 to 10 to the 5 solar mass per parsec cube. The problem with this is that mass function is unknown. You need real simulations to say anything about it. And for the most important point is that do mini clusters merge to form bigger mini clusters? And what is the survival rate of existing mini clusters? So you need real simulations to give you an answer. And often these simulations, they stop much earlier. They don't do it too much in the non-linear regime. But for the purposes of this talk, I just assume it's a delta function peaked around some mini cluster mass I put by hand for convenience. So roughly the surface density power spectrum, which is defined as this quantity, where rho is the profile, which we assume NFW, this is the two-dimensional profile, is an integral over that. And these are column densities, meaning line of sight densities of gravitational potential, so to speak. And then the lensing convergence is defined as this parameter delta. It goes this way. The important point is that it goes as mass to the 1/6 and density to the 1/3. So the claim is that given current sensitivity of caustic lensing events experimentally, one can probe lensing convergence values of roughly 10 to the minus 3. That means one can probe, these corresponds to density of 10 to the 5 solar mass per parsec cube, and this corresponds to 100 per fraction of dark matter of 0.1 and an initial mini cluster mass of roughly 10 to the minus 9 to 10 to the minus 15. So this is 10 to the minus 15, this is 10 to the minus 9 solar masses. And this is for a different central density. Since I'm running out of time, I won't talk too much about it. I want to come to the money plot, which is, so this is the possible exclusion one can put on the mini cluster mass versus the density, the central density of the mini cluster. And QCD axions are predicted to exist in this region, roughly around 10 to the minus 12 to 10 to the minus 9 solar masses. And the lensing events can, in principle, constrain this region. And the typical densities varies roughly between 10 to the 3 to 10 to the 5 today. And you see different shades of these things. All of this depends on the details of the calculation. The best thing one can do is this dark line, but it is ultra optimistic. In principle, it will lie somewhere in between these two boundaries. So this upper boundary is set by a hand, in the sense all the mini clusters in the galaxy lens is aligned along the line of sight. When you make that assumption, you basically get a limit coming from the maximum impact parameter of the light that crosses through. And this has to do with simply sensitivities and so on. So in principle, we can be sure of this dark orange region, but the other regions, to be sure, to actually test the QCD axion mini cluster, you need to do a much more difficult calculation. So that is something we are doing with my collaborators, Michele and Andrea. Hopefully it'll come out soon, but not in 2 weeks. So this is basically the outlook. So micro lens, photometric lensing along the caustics can be probes of dark matter small scale structures. So there's a lot of things to do here, lens model implementation and some theoretical work on how to get analytical handle during these caustic crossing events in the diffraction regime. And in fact, something related to machine learning, astronomers have found many new suspected caustic lensing events just by analyzing archival Hubble Space Telescope data with machine learning. But they're yet to be observed. As I said, the time scales are for years, so it'll be another 5 to 10 years before one can really say anything. The other question one can ask is, can this method do better than traditional microlensing for primordial black holes? And again, that is related to all this, how to implement improved lens models. In principle, yes. Optimistically, realistically, yet to be seen. Thank you.
Okay, so thanks for the organizers for giving me this opportunity to talk about this work. Yeah, so I'll be talking about another observable effect of the bending of light, which produces this gravitational lensing phenomena. So that's the beauty of this gravitational lensing phenomena. It produces different types of observable effects, and which can help us to probe various types of granularity or the massive objects that we can have in a particular line of sight. Okay, so today what I'm going to talk about now is another effect of gravitational lensing, which produces an apparent shift in the sky of a particular source that you are looking at due to the presence of any massive objects in general, but specifically I'll be talking about how primordial black holes that we expect may exist in our universe, how would they deflect the sources in the sky, and can we detect it with Gaia Space Telescope. So I'll be talking about what this telescope is, why do we expect these, something about the primordial black holes, and how can we detect using this phenomena of astrometric microlensing. So we know that in very early universe there are fluctuations in the in the there are primordial fluctuations, and we expect that some of those fluctuations, if the density contrast is high enough, they can collapse and they can form black holes. So it is those black holes which we call primordial black holes. That means they are formed in a very, very early universe. And throughout the evolution of the universe, there will be a star formations, galaxy formation, and then there will be a star formation. And today, when we have these galactic structures, and we know that the galaxies are filled with dark matter, we know that some of the fraction of that dark matter will be primordial black holes if they have been formed in the early universe. So the question is, what is the mass of these primordial black holes that have been formed in the very early universe, and what is the fraction of dark matter that we can expect to be in the form of primordial black holes? So that is what these two axes in every plot. So the x-axis is the mass of the primordial black hole. So you usually assume that, let's say, all of the dark matter primordial black holes have the same mass, monochromatic mass function. So that is this x-axis parameter, and the y-axis is the fraction of dark matter in the form of primordial black hole. So there are various observational signatures that you can expect from these primordial black holes, if the mass of, and they basically depends on what are the masses of these PBHs. So if they are very tiny, we know from because of this Hawking evaporations, they will evaporate and they will give us photon signals, or let's say the electron will also come out of it, and they will also emit radiations at a particular energy. So using those observational signatures, people have set constraints on the plane of this PBH parameter space, and there are other observable effect of these primordial black holes, and one of them is the microlensing, and I specifically will be talking about the astrometric part of this microlensing, as Raghuveer discussed about the photometric and the caustic crossing case. There are other observables like gravitational waves. Definitely it will basically deflect the gravitational wave as well. There will be dynamical frictions due to the presence of this granularity in the galaxy in the form of primordial black holes. And of course, if the primordial black holes are too heavy, then they will accrete gases in the galaxy, and they will also give you some signature. And you can people have set some constraints based upon those signatures. So let's focus on this microlensing part, and the work that we basically did here was started with this question that can we detect or exclude the existence of primordial black hole as a dark matter in our Milky Way by using the observations of Gaia space telescopes. So I'll be talking about what this is, but just to give you the idea that on the parameter space of primordial black hole, where there are already photometric microlensing constraints, there are no astrometric microlensing constraints right now observationally. So what we find is the kind of sensitivity that the Gaia space telescope will be somewhere like, it will be sensitive to 0.1 solar mass to a few million solar mass black holes. And we found that Gaia space telescope might see astrometric shift in the stellar trajectories that Gaia is actually observing. So just to give you the brief idea about what this effect really is and how would you really find it using the Gaia space telescope. So typically you can imagine that in a sky, if the star is moving in this straight line with the blue straight line which you can see here, because of the presence of this foreground lens, what would happen is you will not observe this straight line trajectory. What you will actually observe is this distorted and shifted trajectory of that particular star. Okay, so now if you read the axis, and the typical mass that I have taken here is like 10 solar mass. The source is present, let's say, at 10 kiloparsec from us, and the lens is present in the middle of us and the source. In that case, the typical deflection that you see here is going to be of the order of a milliarc second. Okay. There is another effect that you can see, which is of course the photometric one. That means the apparent brightening of the source as the source is moving in front of, in the background of the lens. Okay. So these are the two effects, and that is why there are two kind of observable signatures due to this microlensing. One is this apparent shift in the position of a source, and another one is the apparent brightening of the source. One is the so the apparent shift is really the astrometric microlensing that I'll be talking about, and the other one is the photometric, where you see the apparent brightening. So that typical shift that this astrometric effect creates on a particular on a star, that depends on what is the mass of the lens, definitely, because it will bend light more, and hence it will shift the apparent position of the source more. And also it depends on how far your source is. So further the source is, smaller the deflection would be. And similarly, where the lens is positioned in between the source and the lens. If you combine everything, you get this Einstein angle as a scaling of the shift that would be produced due to this astrometric microlensing effect. So what is important to notice here is that if you want to observe, let's say, something like 10 solar mass primordial black holes from a star which is at a distance of 10 kiloparsec, what is required is you have to measure the position of the source with an accuracy like of the order of milliarc seconds. So that is the minimum, so that is the kind of a precision that you need in order to position a star in the sky. And there your Gaia Space Telescope helps you. So what Gaia Space Telescope tells you, it basically provides you a billion stars the trajectory of the 1 billion stars in our Milky Way, which is around 1% of the total star of our Milky Way. And it gives you the time series data. That means within 5 years it will give you roughly 35 distinct position of a billion stars, which will have an accuracy as good as 0.1 milliarc seconds. So that is the kind of a precision that Gaia Space Telescope can give you. And the typical typical apparent magnitude of a star that Gaia would be sensitive to would be from 5 to 21 magnitude. Okay, so the question that we ask is following: given the resolution, the astrometric precision of the Gaia Space Telescope is about 0.1 milliarc second. What is, like, out of these 1 billion star trajectories, stellar trajectories, how many of them would be lensed by primordial black holes, if you think that the primordial black hole as a dark matter is kind of embedded in our galaxy as in the form of dark matter? That means the dark matter is kind of a granular, and how many trajectories out of 1 billion will be lensed? So that is the kind of a goal that we set up. So just to give you the idea, what are the kind of astrometric microlensing signals that would be induced due to PBH dark matter and will be observed by Gaia Space Telescope. So the two panels here shows the first panel shows the linear trajectory of a star, and there is a lens, astrometrically lensed trajectory of the star, of the same star. So you can't distinguish it because the deflection is of the order of milliarc second. So we take the difference of the two, and that is what is plotted in the lower panel. The different colors here shows a different mass of the primordial black hole, which is a parameter of PBH dark matter hypothesis. And you can see that larger the mass, larger the deflection would be. That is what we expect. So the green one here is 10 solar mass primordial black hole. The magenta one is 0.5 solar mass, and the blue one is 0.25 solar mass primordial black hole. So you change the mass of the primordial black hole, the deflection will change definitely. Now, what is more important here in the context of Gaia Space Telescope is that if you consider 0.1 milliarcsecond resolution of Gaia Space Telescope, these deflection has to be above that threshold in order to be detectable at Gaia, right? And you can see that depending upon what mass we are probing, the mass of the primordial black hole that we are probing, the duration for which it will be above the detection threshold, that will change. Okay, and as Gaia, the nominal time period of Gaia, that Gaia will be about 5 years. So these vertical lines that you are seeing here, the green one and the magenta one, these are really the observational window when the Gaia was actually looking at that star. And depending upon what mass you are probing, you can see that for the blue one, it comes up just above the detection threshold for a very short period of time. That means you will have only one data point within the 5 years, and that is what we call as a short duration lensing event, which is so this window is basically about 52.2 days. So, and the other one is the magenta one. If the mass of the PBH is like 0.5 solar mass, then the duration of the event would be large enough so that you will have a multiple data points of the same star, and you can actually detect those shift in the apparent trajectory. And that is what is and one important thing is, for 0.5 solar mass primordial black hole, the observational window is kind of fixed. You have to observe during the time when it was above the detection threshold. So this is what we call as the intermediate duration lensing event. Now if you look at the green one, which is the 10 solar mass black hole, it is all the time, so it will always be above the detection threshold, but now the issue is the duration is so large that you will only be observing a part of the signal. So that means the observational window can be anywhere during the signal, during which the signal is above the detection threshold. And in that case, you will not be observing the actual, you will not be observing the absolute shift, but you will be observing the relative shift when you are actually observing during the observation of Gaia. So that shift is basically plotted in the third plot, and you can see that the sensitivity goes down because you are observing only a part of the signal, so only the relative signal you will be able to observe. So the main message is that would create different kinds of signals due to primordial black hole, and that is long duration lensing event. So in summary, depending upon what mass you are probing, the kind of signal that Gaia will be observing will be different, and you have to kind of model those trajectories in a different way. So what we did is we calculated what is the probability of this AML signal due to astrometric microlensing signal due to primordial black hole that we expect to be observed by Gaia. So this is the probability that each star in the sky, what is the probability that it will be lensed by primordial black hole. So in order to do that, what we do is so suppose this is the primordial black hole. We know that the star cannot be away from the primordial black hole much, because then the deflection will go down. So there is this threshold impact parameter within which your star has to be in order to kind of create a detectable signal. Now on top of it, we know that these primordial black hole will have a relative velocity with respect to the star, and hence you can imagine in the sky each of the primordial black holes, they are sweeping a sensitive area in the sky. That is what this yellow patch is. And now in order to calculate what is the probability that each star will get lensed by a primordial black hole, all you have to do is you imagine a patch in the sky and you count how many these yellow patches are there in a particular area, angular solid angle, and in a line of sight you assume that within that window there is one star, and you try to find out what is the probability that a star will fall inside the yellow region, okay, which is the sensitive region where you will get the signal above the detection threshold of Gaia. Okay, so in order to find out the probability, the simple idea is you take the ratio of the total yellow area, which is the sensitive area, divided by the gray one, which is the total area in the sky, and you sum over all the primordial black holes in your line of sight, and that will give you the probability that each star will get lensed by primordial black hole dark matter. Okay, so this is really the cartoonic version of this, of the actual calculation, where we take care of the density of the dark matter, that is kind of that we assume is as the distribution of the primordial black hole will be. That is the density of the primordial black hole, and definitely there will be so in general it will be a fraction of dark matter in the form of primordial black hole, so you consider that as well. There will be some velocity distribution, so we assume the velocity distribution is kind of some average value, some 200 km per second. So yeah, it depends on what is the velocity distribution of dark matter, so we embed that as well, because that velocity will tell you how large that sensitive area is. So it depends on that as well. Overall, putting everything together, you get a probability for each star to get lensed and would be observable at Gaia. And now what we did is following. So we know that the stellar characteristics, the characteristic of a star, that you can define as where that is located in our Milky Way. Okay, so that is this RA and declination, alpha and delta, and then DS, where that source is located, and mg is a measure of how bright the star is. So higher the mg, dimmer the source will be. Okay, so that gives you basically in the grid of these stellar characteristics, we calculated what is the probability of a star sitting at that location at that far and with that brightness. What is the probability that it will be lensed by the PBH dark matter, and it will be observable at Gaia. Now on the right side, what you see is what is the distribution of the sources in our Milky Way that is actually observed by Gaia space. So Gaia Space Telescope has already given publicly, there is a publicly available EDR3, early data release 3rd, catalog, which gives you where it has observed and what is the distribution of the stellar sources. So we took that abundance of the sources, and for each sources we calculated the probability, and all you have to do is just multiply the two catalog and calculate what will be the number of lensing events for a given stellar characteristics. So if you look at in a particular bin of alpha and delta, and in a bin of how far that source is and how bright it is, this catalog basically gives you how many number of lensing events that you can expect to be observed by Gaia within 5 years. Okay, so now you can basically sum over all and try to find out what will be the total number of lensing events that will be observed by Gaia. Now that will depend on two things, which is the PBH parameter space, that is the fraction of dark matter in the form of primordial black holes, and what is the mass of the primordial black hole. So you sum over, basically you sum over this whole catalog, summing over alpha, delta, and ds and mg, and you get the total number of lensing events. So what we did is we now vary the fraction of dark matter parameter and the mass of the primordial black hole parameter, and we see that how many lensing events that Gaia would be observing. And what we get is this this histogram, 2D histogram, where you can read from the color bar what are the number of AML events that we expect to be observed by Gaia, and here you can also see the sensitivity of Gaia Space Telescope on this parameter space. Now the lower cutoff you can imagine, because if the mass is very small, there are two things. One is the deflection will be small because the deviation of the light would be small, and the second thing is the duration will also go down. Okay, so because the two measurement of a particular source that will take roughly around 52 days for Gaia to actually observe the same star. So you can't have any detectable event below that time scale. So the duration of the time events will also go down. So that is why there is a lower cut. The upper cut will also be there, because if your mass of the primordial black hole is too large, the number density will go down, and hence the probability to find a black hole in the foreground of a star, that will go down. Okay. One interesting feature that you can see over here is that this yellow star is really the parameter space of primordial black hole that you require. If you assume that all the gravitational waves that LIGO Virgo have actually observed yet till now, they are all coming from the primordial black holes merger. So if you assume that, which is definitely not a realistic scenario, but in that case, what is required is this parameter space of the primordial black holes that should be there in order to explain all the events. But you can see that the Gaia is also kind of falling in that window. So in conjunction with the events that you observe with LIGO, Virgo, and now Kagra, you would be able to kind of rule out this possibility that whether the events that you are observing at LIGO, whether they are really have primordial origin or not. So with this I'll conclude. So we basically predicted how many number of astrometric microlensing events that Gaia will be observing. We kind of classified the signals that PBHs will be actually inducing in the stellar trajectories in terms of the duration of the events, which depends on what is the mass of the primordial black hole. And we found the distribution of the lensing event in the Milky Way, depending upon what star you are considering. You can basically read these catalogs and find out what will be the lensing event rate. And so we got the sensitivity region of the primordial black hole so that we can further refine it out, which basically goes from 0.4 solar mass to 10 power 5 times 10 power 7 solar mass, with the peak sensitivity for the 10 solar mass black hole. And it can be as small as 10 power minus 4 fraction of the dark matter in the form of primordial black hole. So thank you. If there are questions, suggestions, comments, we can discuss.
Okay. Thanks, Himanshu, for the awesome talk. So again, we'll take questions after the talks, and now Arun will talk about exotic compact objects.
So it's very nice to be here. It's nice to meet so many colleagues and friends and have all the interesting discussions. So let me start by thanking the organizers for this wonderful conference. What I promised Nirmal is that I'll give a very brief, short, semi-pedagogical even summary of some of the theoretical solutions our community has been interested in over the past many years, if not many decades, some of which makes a nice connection with what Raghuveer and Himanshu talked about in their excellent talks on how to use both photometric and astrometric lensing. So these objects generally are called exotic compact objects. Now, exotic could mean many things. For example, they could mean unusual astrophysical objects. So like neutron stars which have gobbled up too much dark matter, for instance, or what are called dark stars, which have been proposed by Catherine Fries and group, where basically the energy generation mechanism is completely from dark matter annihilation. They also include other beasts like magnetic black holes, magnetic primordial black holes even. There are other even more interesting objects. I shouldn't say even more interesting, but equally interesting objects like cue balls and so on, which people have looked at. I will highly recommend one of the reviews written by Nirmal and Bramante on dark matter and compact stars. It's a very excellent review. I encourage especially the students to go have a look at it. I will mainly focus on this last category, which goes by the name of non-topological solitonic objects. Okay, so the question is, what is the theoretical characteristics of such astrophysical objects if they ever form? Maybe they don't exist, but if they exist, what kind of theoretical characteristics they would have, and how might we detect them using photometric or astrometric lensing, as Raghuveer and Himanshu kind of alluded to. Now, some of the salient aspects of these objects can be understood using very simple principles. So, these objects are basically scalar fields in some configuration, in some macroscopic configuration. And the word non-topological in the earlier sense just meant that there is some kind of a conserved quantum number, a conserved charge, which gives stability to these objects, as opposed to topological solitons whose stability is kind of because of some topological charge. Okay, here there is some kind of a U1 charge, etc., which gives them a stability. So let's try to understand some scaling relations using simple ideas. So as you can imagine, if these are made of bosons, there is no longer something like the Fermi degeneracy pressure to support them against gravitational collapse. So basically the fundamental principle which stabilizes these objects is the Heisenberg uncertainty principle. Okay? So imagine there is some scalar particle of mass m which is confined to some size 2r. So the rough velocity scales in this fashion from the uncertainty principle. So the kinetic energy per particle half mv square, assuming non-relativistic speeds at the moment. The kinetic energy scales like this. The potential energy of a self-gravitating system goes like some g m square by r. The total energy therefore is this. There is a capital N here, where capital N is a number of these scalar particles which is in the star. So capital N is roughly like capital M divided by small m, where capital M is a putative mass of this boson star. Now if we minimize this, we get that these objects characteristically have some radius which goes like 1 over m square g Newton times whatever the mass is. So interestingly, if you have larger masses, these objects are smaller in general. Okay. Now this also actually furnishes a limit for the maximum mass of these objects, because as we saw in the earlier slide, the characteristic radius or size of these objects is inversely proportional to m. So as the mass increases, the radius shrinks, but you can't have the radius shrink below 2m, which is the Schwarzschild radius. If you pack that much energy into that smaller size, it will actually just become a black hole. So there is a lower limit which actually gives us a maximum mass for these objects. Okay, this goes like 1 over g Newton times m. G Newton is like 1 by m Planck square. So here the scaling is like m Planck square over m. Okay, and this mass limit is sometimes called the Corp mass limit. And just to contrast it with typical astrophysical objects like the Chandrasekhar limit, there the scaling was like m Planck cube by m square. This goes like m Planck square by m. Of course, this is a very rudimentary back of the envelope calculation. For example, there have been assumptions which I have not even mentioned. I've just swept it under the rug. For example, here there is an implicit assumption that the pressure inside these objects is isotropic. And this is not always true. But in cases where you can assume isotropic pressure, etc. The Kopp mass limit and the scaling which we talked about is a pretty good approximation, up to some order 1 factors, etc. So, as I alluded to, how are the solutions? Okay, now if we try and compute the theoretical profile of these objects more comprehensively, more precisely, what are the kind of challenges we usually face? So, one of them I will motivate by reminding us about the usual Tolman-Oppenheimer-Volkoff solution. So, there if you had a spherically symmetric metric, the perfect fluid assumption was a good toy model to work with, at least initially. And you start with some perfect fluid assumption. Here it's isotropic, the P radial, P theta, P phi components are all the same, okay, when you extract it from the T mu nu. And you can, with some standard techniques, solve the Einstein equations using this perfect fluid and their equation of state in a standard way. Okay, and one gets the Tolman-Oppenheimer-Volkoff equation. Some of the simplification was because it's isotropic. The pressure was isotropic. Okay. Now, in the case of a general scalar field theory, okay, from which you're trying to construct these macroscopic astrophysical objects, boson stars, the energy momentum tensor, we look at it, generically they will not satisfy the condition that the radial pressure is same as the tangential pressures. Okay. In cases where this is a good approximation, even the scaling which we derive, like the Kopp mass limit up to order 1 factors, is a good thing. But generally this is not the case. So what this forces us to generally do is we have to actually solve the full Einstein-Klein-Gordon system. Or in the non-relativistic limit, these, become what are called the Gross-Pitavsky-Poisson equations. So this makes it slightly more challenging. What this meant is, for many decades, we knew the solutions only for very special potentials or very special limits, etc. There have been some developments in the last few years trying to get semi-analytic, if not fully analytic, solutions to some of these systems. So some of these developments were from Arvind Rajaraman and Felix Kling's group. So they found a systematic way to start from the Gross-Pitavsky-Poisson equation, rewrite it in a particular way using some scaling symmetry which they found, and basically patch up solutions at various regions: interior region, intermediate region, outer region. They found a particular prescription to do this, which led to a lot of excitement, that rather than looking at exact solutions which many times involved potentials which could not be fully motivated sometimes, there was some hope that at least semi-analytically you could actually study the theoretical solutions, if not semi-quantitative solutions to some of these objects. Another class of objects which again fall under non-topological solitons, which can be thought of as a particular limit of boson stars, what is called the non-gravitational limit, in the sense that gravity can be neglected compared to their self-interaction, the scalar self-interaction, goes by the name of cue balls. This was first introduced by Sidney Coleman in the early 80s. And there have been many works related to cue balls since then. Again, so cue balls, what distinguishes them is you can have boson stars with even no self-interactions. Okay, just the Heisenberg uncertainty principle can stabilize them. Now you can add something like a mass term, you can add something like a lambda phi 4 term, etc. Okay, but cue balls are very distinct in the sense that cue balls can occur only if the scalar potential satisfies this relation, in the sense that the u over phi square is actually a minima in the field space. Okay, so one way to think about this is that m is like the mass of the fundamental quanta, the fundamental scalar particle. The u over phi square is like the mass of the fundamental quanta in this other local minima. Okay, so in some sense, whatever is a fundamental quanta here cannot energetically disperse and form the phi mesons. Okay, so if such a condition is satisfied, you can have Q-ball solutions. But this dictates very particular form, very specific forms for the scalar potential. And they're called, Coleman called it Q-balls because the energy is like, Q is like a conserved, Q is the conserved charge here. So it's also kind of like the particle number. So energy to leading order is like particle number times some fixed quantity. So it's kind of like we put some marbles together to form this macroscopic object. And whatever is the correction just depends on the gradient of the thing. So for a long time, and including the solution which Coleman showed exists from his typical arguments, clever arguments like overshoot, undershoot, is that you can have thin wall Q balls where this transition region is kind of steep. Again, in the last few years, and of course, people ran with this, they found exact solutions in 1 + 1, so on and so forth, and some of these are very interesting. In the last few years, again, there have been a lot of development in coming up with very accurate semi-analytic solutions to arbitrary potentials. So, for example, the sextic potential, no good theoretical understanding was present until again few groups started looking at them, and the details are interesting, but for lack of time I will not talk about them. I'll be happy to chat offline. So again, the agreement is kind of quite spectacular, which opens up a whole new area that one can actually now explore both theoretical and observational consequences of certain distributions, mass distributions, which earlier we could not. Like for example, until very recently, people had only studied thin wall Q balls, which are well approximated by a step function. But then neutron stars are also well approximated by step function, density profile, so on. But now you can explore more exotic possibilities, and again the agreement is very good, and you can use things like photometric microlensing to put constraints on them. You can even put theoretical bounds on Q balls, like how big can a Q ball be? What is a maximum radius? There's actually a minimum radius and a maximum radius for Q ball astrophysical object. So I'll stop here and open the panel for any questions.
Okay, thanks Arun for the excellent overview. So we have 15 minutes left. So if people have questions, please ask. Yes.
The place where from Gaia data, that primordial black hole mass you were discussing about constraining, is it possible to model those black holes as some sort of Kerr black hole and put an exclusion limit on angular momentum mass plane from that observation?
And then the next two leading order will be square plus 4. So it will be suppressed by that extra leading. But if let's say the angular separation is small, so that you can actually see the effect of spin. In that case, you would be perhaps able to see the effects in the astrometric shift. The other thing is, if they are very close to, if the angular separation is very small, then there might be a chance of a kind of a multiple images of the
of the source. Basically, those are relativistic images.
I see.
But those are like very rare kinds of image phenomenon that you can.
So those sort of things are not interesting for the parameter space of the theory you want to probe at the end of the day.
They are interesting. So as I said, finding out the spin of the primordial black hole through astrometric microlensing is a higher order issue. Primarily, there will be a shift due to just because of the mass. So once you detect it, and then you can search in the signal that whether there is a signature hint of measuring the spin or not. You mean the photometric? Yeah, in photometric, anyway, in photometric, the angular separation, the impact parameter has to be small enough, like within an Einstein angle. For example, in astrometric microlensing, the typical impact parameter for which you get astrometric microlensing signature is like 1,000 times, or actually 2,000 times the photometric impact parameter. So, typically you get astrometric shift for a larger angular separation. But for photometric, you will get the smaller one, and for that, I guess you may see the morphology and signatures of astrometric.
Thank you.
Yes. Yeah.
So I was wondering about this cue balls thing, that the potential that you showed. So, is it possible that if the field is localized at some higher minima, then it tunnels to the lower minima, and that affects the evolution of the cue ball somehow? Maybe.
So here the point is that you need something for it to tunnel to.
Yeah, so
right, which is also
lower minimal.
Yeah, no, but here the cue ball cannot. It's even stable under quantum tunneling because there's nothing for it to tunnel to. Okay. See, because tunneling still conserves energy. Right?
Yeah.
So, but there's nothing for this cue ball to tunnel to because of that stability condition, which is required for the existence of cue balls. It can, for example, tunnel and then become individual scalar mesons.
Okay.
That can happen. Now, what can happen is if there is a coupling to fermions, etc. So this, like Anish Manohar, etc. have studied. Then you can have some decay of cue ball. Then you can ask questions of stability, metastability, etc.
Okay.
Yeah.
So,
but quantum mechanically, it's even quantum mechanically stable because it can't tunnel to anything.
Okay. Thank you.
Actually, I have a question for two different talks. So first question is for Professor Raghuveer. So you were talking about probing masses 10 to the power minus 15 to minus 9 solar mass axion mini clusters. So I was wondering whether can we distinguish signal what we call it caustic lensing signature for PBH and the axion mini cluster. What would be because we are talking about very small mass scale.
Technically you cannot, because it just depends on GM over lambda.
Yeah.
So if the mass is the same, similar limits would apply. The question is how these things form what's the density? That is the question. But just by assuming same density everything, it's very hard to distinguish.
Okay. And the other question is, I have written down some questions. So you used NFW profile, but in the literature for axion mini cluster, if we follow the press sector formalism, the density profile turns out to be a power law, minus 9/4, right?
It doesn't matter too much. Because it just depends on the so-called average central density. That doesn't depend too much on the profile. So once you fix the mass,
And if we have axion mini cluster, it is natural to form solitons as well, right? The boson stars in the center of these mini clusters. So will it modify somehow the signal because we have compact object in the center of these mini clusters?
So it just depends on the total mass. So if the whole thing is solitonic or not, or even if the core is solitonic, it shouldn't really matter. Unless it interacts with photons, and that's a different story.
Okay.
But just from that argument, it shouldn't matter too much.
Okay. Thanks. Yes, for Himanshu, I have another question. So you talked about in the stellar graveyard where the mass of the PBH is of the order of tens of solar mass. So there, the gravitational lensing signature requires a binary to form, but astrometric microlensing, we are modeling like a maybe single lens. So will there be any effect if we consider double lens like in the signature of AML?
Yeah, so we didn't consider the binary lenses, but you do expect some fraction of the total events might be coming from the binaries. Their signatures will be a bit different. In fact, would be more prominent to actually observe. Yeah, so definitely those will be like subdominant events. So out of, let's say, 10,000 events, maybe a few of them, I don't know the number, one has to work it out, but some of them are going to be the coming from binaries. But you have to model it like how many PBH pairs would be close enough in order to form the binaries and so on and so forth. And you can count like out of these many lenses, how many of can be binary lenses, and then you can calculate the signatures due to them.
So for binary lenses, do we expect the signal to be more strong, or like it will weaken?
Yeah, so whether the signal as observed by Gaia is more strong or not, that is something one has to see, because the Gaia is not only observing a straight line trajectory of a star, which is kind of a simplification that we did in our calculation. Our Gaia is basically moving with the Earth. It is at the L2 position. So it has this parallax effect of each of the stars. So within 5 years, you will see 5 kind of a helical structure in each of the star. And that bending, basically that kind of curves that you observe from Gaia, that can mimic like a lensing signature. So you have to separate it out. And in the case of binary lenses, it will be even more prominent issue, right? So this is the drawback. But the another thing is, definitely you will have if you have a binaries, you will have a kind of a double deflections, right? So that will be the plus point. So one has to see which one will be more like ultimately will turn out to be beneficial or not. So those calculations I don't remember if anyone has done, but it will be interesting to look at those binary lensing signatures due to primordial black holes as well.
Okay, thanks.
Yeah.
So is the data from Gaia or say JWST available to people outside collaboration to analyze, or do you have to wait till somebody from the collaboration analyzes the data? Especially since you are looking at some specific sort of transient signals, and maybe nobody in the collaboration might think of analyzing that. In that case, is it possible for you to get access to data and do something on your own with it?
Yeah, so for Gaia, I know that so there are publicly released kind of a one snapshot of the galaxy, which right now we have. The time series data would be available within 1 year or two. So it has already observed the our Milky Way for 10 years now. So it started at 2013, 2023. It has completed 10 years of observation, and the time series data will be available 2024 or 25 or 26.
It will be available after a gap of 10 years. Is that the?
Yeah. So it has just finished its observational period of 10 years, right? Mm-hmm. So now it will take some time to kind of compile everything, and then the time series data will be publicly available. It will not be complete raw data. It will be processed, but it will be enough information so that we can do such kind of a study of astrometric microlensing. And for
So for JWST, there is no collaboration. So it's basically, if you want to observe something, so every year there's a call called the General Observers Program, where you have to write a proposal, like it's a short proposal, 2-3 pages, asking them to do something. So then the data related to that particular observation will be proprietary for 1 year by policy. And after 1 year, it is public. You can find it in standard astrophysical databases. So that depends on who's writing the proposal and how big their program is. Because some of them ask for a lot of observation time, but some people ask for small observation time over a period of years. So it depends, really. And also whether, if a topic is hot, then it depends a bit. But the Hubble data is already publicly available. So that anybody can use. Yes. But you should know how to extract them. No, actually, every observation is marked by a date. This modern Julian date, or what are this epoch, J2000 epoch. So it's listed by date. The same point, after processing at each observation point, is a table. You have to convert it to whatever time you want, and you can use it.
Yeah, so my question is to Raghuveer. So we were discussing if astrometric signals can distinguish binary primordial black holes, but how plausible is it to differentiate the signals in the photometric lensing for binary systems?
You mean binary sources?
Binary lenses.
No, but this is a galaxy cluster. So inside the galaxy cluster, you have put smaller lenses in it, smaller objects in it. If it's really binary or not shouldn't matter too much. If they're all aligned along your line of sight, you get the maximum signal. Yeah, exactly.
You talked about all this cue ball. So does it make sense, like talking about cue ball evolution in a de Sitter background where you model the cosmological constant and then compute like tunneling, etc.?
So I should clarify one thing. So what Coleman called cue ball and what has been called cue ball are actually flat space-time solutions.
Okay.
So that's why, so in some sense, cue balls are a subset of boson stars in the non-gravitational limit. And so in the Gross-Pitavsky equation, there is a m gravitational potential times psi term.
I see.
So that should be subdominant compared to the self-interaction term.
Assumption.
So in some sense, these are like flat space-time.
Okay. I see. Okay.
Solid.
So, if there are no further questions, let's thank all the speakers again for the excellent talks and discussions.